Okay, hello, welcome to the progress update video of the Automotive Design Project Energy Challenge Group 1. I will give you a short introduction since I'm the communication manager of this group. Well, first of all, the background. We're doing this project for a company called TUE Vehicles. They've given us a challenge to design an optimal energy efficient driving strategy for their car, and they've given us a 1 in 5 model so we can perform tests on it. And this project is a great way to put what we have learned to practice and to learn how to work in groups and review each other, and also it's a good way to learn how to present and write technical reports, which are very useful skills in the future. Well, like I said, the problem statement is to design an optimal energy efficient driving strategy for their electric car. Well, to do this, we first have to find the environmental effects on the car, so the forces acting on the car and their magnitude. And then after that we have to find the internal efficiency of the car, so powertrain losses, and with all that we can then calculate and design an optimal energy efficient driving strategy. Well, we will do this by performing several experiments on the model car, and once we've done that we can use that data and perform our calculations. Well, our work approach was basically very simple. We started with dividing the work into subgroups, and each subgroup has to work on a specific part of this project. We have made several subgroups which we will discuss later. For this it's very important to work together, and that's why teamwork is a very big part of this project. We have to keep each other updated constantly during this project on what we're doing, and so we can help each other and we can make sure everyone does what they have to do. Then very important for that is planning. So we have to make sure all the deadlines are met and everyone has their work finished in time. There's one subgroup that we won't be discussing during this presentation, and that's our optimal driving strategy subgroup. That's simply because it is not possible for that subgroup to do all their work right now, since the experiments have to be done first and the data gathered from those experiments has to be used so we can calculate and design the optimal driving strategy. This subgroup will, however, present their work in the final design video. We have weekly meetings so we can discuss our work with each other, and this is a great way to make sure everything is done in time. Then what are we going to talk about today? First of all, the rolling resistance subgroup is going to tell you what they've done and show you what's in the planning. Then the aerodynamic drag and dynamometer subgroups are going to talk about what they've done, and we're going to finish off with the speedometer subgroup. Well, I will now give the word to Koen for the rolling resistance subgroup.
Rolling resistance is part of the tank-to-wheel analysis, meant to calculate the energy losses in various parts of the car. Rolling resistance, air drag, and the dynamometer. For rolling resistance, I've mainly been focusing on the test plan itself. Well, the test plan looks this way. First, the car needs to be prepared. There will be an Arduino Duo which has been programmed with the default program that logs the speed at various time instances on an SD card. There will be an RPM sensor present that will send pulse to the Arduino every certain rotations, and this will be computed into a velocity that will be logged in an Excel sheet. Furthermore, there will be an electric motor that can be easily attached and detached, so that we can test with and without the resistance from the electric motor. This will be the test construction. There will be a slope that will create an initial velocity, and then there will be the floor at which the car will be coasted down. From the top of the hill to the far end, the speed will be locked, and with the time differences and the velocity at certain time instances, the acceleration can be calculated, or actually the deceleration on a flat surface. It's more convenient to use this service because it's also the service we're going to be driving on, and then we won't have to bother about the adhesion between the tires and the material that this service is made from. On the wood we would have to do so, but it's not really relevant because we won't be driving on wood. Well, with this equation we can transform the data we gathered into the actual rolling resistance. From the experiment we will get velocities and time intervals. With that we can calculate the acceleration on any time instances in the experiment. The mass of the car can be easily computed with the pair of scales. With that we can calculate the total resistance the car experiences in its deceleration. With the electric motor attached, the total resistance consists of the resistance within the electric motor, the drag force, and the rolling resistance. And of course, if you take out the electric motor, you won't be taking that into account, so we will be testing both with and without. So with the difference we can compute the resistance within the motor. The drag force will be calculated in the experiment that is going to be expanded upon in the next presentation. And the rolling resistance is of course the variable I'm going to mainly be focusing at. So from now on, the test plan needs to be finished. After that, of course, the test itself needs to be scheduled. We're planning to schedule the test as early as possible, so there will be enough time to finally lay the link between the data and the actual result, and subsequently the test report can be written. So now I'm going to give the word to the drag force team.
So the next part will be about air drag and what we did. So first of all, let's tell the progress we've made. So we made the test plans version 1, and we also encountered a few small problems with that because the feedback wasn't really too positive, but we're working on that now. So first of all, as told before, we need to calculate the air drag, and we can do that by this equation. It basically says the air drag force is 1/2 times the air density times the coefficient of drag times the frontal area of the car times the velocity of the car squared. And in our wind tunnel that is situated here at the TUE, we can determine F drag and the velocity of the car, and the setup, or with that we can calculate the coefficient of drag, because we can also determine the air density and the frontal area of the car. So the setup of the experiment will be this. This is the wind tunnel, and the wind is basically going from here down here where the car is situated. And in this picture you can see that the car is standing on a platform which is suspended from the air. So it basically is a frictionless surface that the car is standing on. And with a force sensor attached to this platform, we can read the force. So that is F drag. And also with a pressure meter, we can measure the pressure between here and here. And with that we can calculate the wind speed by using an equation. So there will be a few differences in our experiment, and that's because we have a rear wing and a front splitter, as pictured here, and we can attach those to the car. And in the first experiment we'll have none of them equipped, and then we'll do it again by only having the rear wing equipped, and then again by only having the front splitter equipped. And then we can basically see what is the most efficient setup for us. So for the planning, we're first working on the test plans version 2. We'll hopefully finish that soon. And after that, we'll do the experiment, of course, and then get the test results and make the midterm report. So I will now give the word to the dynamometer group.
Okay, I will first talk about the dynamometer. Okay, I will first talk about the dynamometer. At first we've done research into the dynamometer itself and how it works, what values we need to put in. So, for example, we put in like the values of like F-road load, wheel speed, and distance we travel. These values will all help to calculate the total power usage of the car during one specific test. We've divided our whole testing procedure into 3 separate tests: test 1, test 2, and test 3. In test 1, we will disconnect the motor from the battery and use only put in a wheel speed. This will give us the resistance of the tire, so we can calculate it. I visualized our calculations in this Sankey diagram. So P-rotor is like P in, and P-friction is the friction of the gears, and P-r is the traction tire, the power loss due to traction tire force. In test 1, we will skip the P-friction because that value is going to be really low, so we can almost neglect it. And this will help us to calculate the tire resistance on the roller. Then we've done test 2. In test 2, we wanted to calculate the overall P in and P out. So we measured the P in, so the power from the motor, and that's also the power we put in via the battery. Then we've also measured P out, and that's the P of the dyno, so the power we measured the dyno. With this we can make a general calculation on how big the total amount of resistive force on the car will be. Then we've done test 3, which will enable us to measure the energy usage of the electrical components, of solid electrical components. With all these 3 tests, we can subtract test 1 and 2, test 1 and 3 from test 2, which will give us the values of PG, so the power loss of the gearing, and the power loss of the motor. There were a few problems we encountered during making the test plans. The main problem we encountered was like the overall vagueness of the project. This may be due to our misunderstanding. For example, we made a graph of the energy efficiency using examples from the web. So we used a similar engine also 1/5 scale and a similar kV rating to calculate the engine efficiency, but our supervisor told us this wasn't needed. We also made like a few other graphs, but those were also not needed. Okay, well, the planning. Well, in the future, we hope to get a green light on test plan version 2. We will try to improve it. After we got a green light from test 2, we will start with experiments. Those will probably be done in the few upcoming weeks. These experiments will give us the ability to calculate power in and power out and total engine efficiency. Furthermore, in the next coming weeks, the next week we'll start working on the midterm project with midterm report.
So I'm going to give you now some information about the speedometer. Now the goal of this is to actually indicate the speed and to look what the optimal velocity is and how close you are to it when driving it for mainly the last week when we are going to drive around the track and test our optimal driving velocity. Now what we have done already is basically made a bit of a project overview to get to know what we had to do and when and where. And then because neither of us had any experience with the Arduino, we started to look online for some solutions and some help and tips on the Arduino, and we started to get the hang of it. And then soon as we learned how to use the Arduino, we started trying to read the RPM pulses. Now, as Koen already told you, there is a RPM sensor in the car, and basically what it is, it's an extra gear mounted to the axis, and which has two magnets in it, and every time a magnet passes the sensor, it gives a pulse to the Arduino. So we tried reading it, and after a while it worked by setting the pin which was connected to the sensor as an input sensor. And after that, after we got a 0 when there was no magnet in front of the sensor, or a 1 when there was a magnet in front of the sensor, and after we did that, we tried calculating the time interval between those two pulses, and with that we tried to calculate the speed by dividing distance by velocity, and the distance we measured just by the circumference of the wheel. Now, there were some problems we encountered during the progress. For example, there was the problem with the gear ratio. Now we were wondering if the gear of the actual sensor was rotated at the same speed as the actual wheel. Turns out it wasn't the case, and we had to count every tooth on each wheel to calculate the gear ratio. Now we found out that it was a 1:3 gear ratio, so we added that into the calculations for the speed, and now we got the correct speed. Now another problem we are still not sure about is the speed accuracy. That is how accurate is the speed of, or the between two pulses. So to solve this problem, we tried to take an average over 4 pulses, and the average speed will be displayed when it's calculated. And we think this is quite a good solution, but we're not really sure if we should tweak it a little bit more. Now, for the planning of the speedometer, what to do next, we are trying to confirm actually the displayed velocity by using an oscillator, and just calculating by hand how much the speed is at a certain time. After that, we are going to try to look into how to program the LED strip, which will be showing the speed. And we don't have any experience with LED programming, so we have to look really into it. And after we are able to actually control the LEDs and make the color change or make them blink, we will discuss furthermore a bit about how to indicate the actual speed. So a solution for it is, for example, if you have reached the optimal velocity, which is calculated by the team of the optimal driving strategy, the lights, for example, will all turn green, and if you go under or above it, the lights will change color or will just go out. Now, after we've done all that, we will do some final testing to check if everything works. And now I will give some last words to Tiggo.
Well, in conclusion, we can say that we have done a lot of research, and now it's time to perform the experiments and to interpret that data, and with that we can calculate and design an optimal energy efficient driving strategy.